This is the world's first mass production factory for solid-state batteries. We got invited inside to see something no camera crews have filmed before.
But here's the thing, we've had so much hype about batteries, especially solid state, for a while now. Donut Lab, which we covered recently with zero proof. QuantumScape is different. They've actually worked with partners like Volkswagen, and they've published papers showing how their stuff works. And when it comes to the claim of solid state battery, there is a caveat. And in this video, we're gonna go in there and figure this all out. I'm Ricky, and this is Stupid Da Vinci.
This video is brought to you by Scribe. In this video, we're going to cover these following checklist items to see if this is the real deal. 1. What part of the battery is being revolutionized? There's the anode, cathode, separator, and electrolyte. 2. Can they scale up manufacturing of the solid-state separator? 3. Can they automate the entire cell and pouch manufacturing like today's batteries? 4. Does their business model make sense? 5. Is this a revolutionary moment that will change the trajectory of future battery development? And finally, 6. Is it a true solid-state battery?
So why should we even care about solid-state batteries?
Right now, the battery in your EV or phone has liquid in it. That liquid is flammable. It limits how fast you can charge, and it's one of the driving factors in EV price and range. Solid-state batteries promise to fix all that.
To get high power in a solid-state battery, lithium needs to move through a solid material as fast as it can move through a liquid. And it's not moving through holes in the solid in the sense that like there's Swiss cheese with holes that a material's moving through. It's literally lithium dissolving onto an atomic lattice of a solid and hopping through as atoms through a solid, and it can do that faster than it flows through the liquid. In 2025, we said, this process works, make it faster. And so what we're showing today is the highly automated version of that battery cell assembly process.
They showed us a real production line making real batteries that are going into real vehicles. And here's the spec that made us pay attention. This battery charges from 5% to 80% in under 15 minutes. Not in a lab and not under perfect conditions, but in real-world discharge rates that actually matter. But that's not even the most interesting part. See, QuantumScape brags about 2 specs that no other battery company has ever mentioned before. And when we dug into why, we realized that those 2 numbers reveal everything about how they actually pulled this off. And we'll get to those, but first, you need to understand the problem they solved. In a traditional battery, you've got lithium ions bouncing between 2 sides. Think of the anode, the negative side, as a locker room. When you charge the battery, lithium ions fill up the lockers. When you use the battery, they leave. The locker room itself is usually made of graphite. It just sits there, taking up space and adding weight, waiting for lithium to come and go. QuantumScape said, what if we delete the locker room entirely? In their battery, when it's fully discharged, there is no anode. Nothing, just empty space. When you charge it, pure metallic lithium forms directly on the surface. Every single atom of lithium is actually being used to store energy, no wasted weight or space. This is why their energy density is double what you get in a conventional battery.
What is like the gravimetric energy density that your pack is able to, or your cell is able to achieve?
Yeah, our cell is 301 watt-hours per kilogram and 844 watt-hours per liter.
Okay.
State-of-the-art in lithium ion, for reference, would be mid-200s watt-hours per kilogram, and the best would be low 700s watt-hours per liter.
That's not incremental improvement. That's like a generational leap.
Now, we love coming on site to make these videos because we learn so much. But whenever I travel, that means the other team members have to do some of the jobs that I normally do. And I'll be honest, our documentation and SOPs haven't been great in the past.
But not anymore. Scribe is the most amazing way I've ever seen to document processes and share knowledge with anyone. Check this out. I normally upload our videos to YouTube, add descriptions, links, and thumbnails and so on, but it's easy to miss steps, and it's critical as a YouTuber. Now I can capture a Scribe, which records my clicks and actions and automatically creates a step-by-step guide in real time as I'm doing it. This saves me hours of work, and it's the easiest, fastest way to document my processes. You can share your Scribes in seconds as a PDF or link, add your teammates, whatever works for you. Plus, if things change, like the tool or the UI, just update your Scribe and it automatically updates for all the team members using the same link. Scribe is so good. Now when I play IT support for my parents, I don't struggle with video chats. I just create a Scribe. The use cases are seriously endless, and the interface and UX are amazing. 10 out of 10. So level up your workflow and unlock serious time savings. Head over to scribe.how/2bit or check the links in the description to try their Chrome extension free and get even more features with Pro today. Huge thanks to Scribe and you. Now back to the show. here's where that death spiral actually kicks in. If you delete the locker room and use every lithium atom for storage, you have zero margin for error. Most battery companies add 20 to 50% extra lithium to their cells. It's the buffer, because every time you charge and discharge, you lose a tiny bit of lithium to side reactions. QuantumScape can't do that. They have no buffer. Every atom lost is permanent capacity gone. If you lose just 1/10 of 1% of your lithium every cycle, your battery is completely dead in 223 cycles. That's less than a year of normal use.
In a lithium-ion battery, all the lithium is stored in the cathode material, and that's the lithium that charges. There's extra lithium by design, as you were saying, because that lithium has to create the anode candy shell coating on graphite particles. Some of the lithium is consumed. In our battery, we don't create that shell coating called an SEI. Our material is very stable in contact with lithium. The term is Coulombic Efficiency, which is how many lithium atoms or electrons shuttle back and forth relative to how many are lost to the sign reactions, as he described. Our Coulombic efficiency is very high. It's actually difficult to get electronics to measure with that precision. It's north of 99.996%. So very, very little lithium is lost in our battery. Our battery does fade gradually, and that's due to the cathode, which is a fade that's present in lithium-ion batteries. But the major reason that you have to replace your cell phone every few years because the battery is failing on the anode side. That anode candy shell coating cracks and needs to be reformed, which consumes extra lithium.
When you discharge a lithium metal battery, you're stripping lithium off the surface. If it doesn't come off perfectly even, you get voids, air gaps. The battery loses contact with itself and stops working.
To keep the solids in good contact, pressure is typically applied. And talking about very high amounts of pressure. What's common is 10 atmospheres, 20 atmospheres or more, enough that would crush most materials. That's applied to just keep the materials in contact. The way it's applied is with a giant clamp or pneumatic press to press things together. Something like a phone is just too thin for that to exist inside. You need a big device like a car, and even then a lot of the automotive pack would be a fixture. One of the things that we've worked quite hard on is to understand why solid-state batteries typically require pressure and to design an architecture and a material system that doesn't require that high pressure.
But here's the trap. When you apply pressure lithium metal, it grows these tiny needle-like structures called dendrites. They're like little spears that punch through the battery and short-circuit the whole thing. More pressure means better contact, but more dendrites. Less pressure means fewer dendrites, but worse contact. And this is the death spiral. And it's why everyone said solid-state batteries were impossible. So how did QuantumScape solve it?
So we did have to understand from a pretty deep way how dendrites, why dendrites form to be able to stop them. We did release a paper last year that describes a little bit of our approach with an extremely high throughput test system where we were able to do hundreds of thousands of tests per year to iterate very quickly, get a large volume of statistically meaningful data. And we showed how we were able over time to improve the critical current density, which is the metric of what charge rate the battery will accept before failing due to a dendrite. And we were able to increase that and push it far beyond what's required in a battery.
Remember those two weird specs I mentioned? The first one is operating pressure, less than 3.4 atmospheres. That's about the pressure inside a soda can. Every other solid-state approach requires 10 to 50 atmospheres of pressure. That's like having a car sitting on top of every battery cell. The second spec is cathode loading.
It just refers to how much active material is in the cathode. And then that directly will translate to how much energy is in the battery. Cathode with small loading is thin or sparsely populated with the active material. So it's a high power battery, but a low energy battery. One thing that's pretty unique about our technology is we can offer really world-class or better than world-class, that is high cathode loading, very thick cathodes, and still do very fast charge and discharge.
6.2 milliamp hours per square centimeter. Now, if you're not a battery engineer, that number seems like it doesn't matter. But here's what it tells us. It means that QuantumScape figured out how to make a ceramic separator that actually works.
Ceramics are often made in a pretty slow, low throughput fashion that's not cost effective to be used in batteries. So we had about a 4-year-long research project to try and speed up the process. We rolled it out in 2 different phases, and the second phase we completed last year. We call it the Cobra process, which was really, I think, a game-changing innovation, both in science and in engineering of ceramics, so that we are able to make the material at the right quality and, more importantly, at such a high throughput that it can be economically effective.
This is their real breakthrough, not the battery chemistry, but the separator. Most ceramics are brittle. They crack when the battery expands, and they can't stop dendrites without massive pressure. QuantumScape developed a flexible ceramic that bends without breaking. It's thin enough to let lithium pass through efficiently, but tough enough to physically block dendrites. And here's the key, it works at soda can pressure. That separator is the reason this entire technology exists. Without it, everything else falls apart. And they didn't just invent the material, they invented the manufacturing process to make it at scale. We're talking about entirely custom-built equipment, machines that didn't exist 2 years ago, making a material that didn't exist 5 years ago. 10 years of development, over 2 million tests, more than $300 million in R&D. But there's one problem they had to solve, and honestly, this one surprised me. Remember, this battery has no anode when it's empty. The lithium forms when you charge it, so what happens to the battery's size? In a normal battery, charging is like putting balls in a locker. The locker room doesn't get bigger. The battery swells maybe 2 or 4%. In a lithium metal battery, the lithium is the anode. So when you charge it, the anode literally grows. Now we did the math on this. With QuantumScape specs, each cell grows about 18.5% when you charge it. Think about that. Your battery pack gets almost 20% thicker every time you plug it in, then shrinks back down when you drive. Well, QuantumScape designed an entirely new cell format called FlexFrame. It's a hybrid, half pouch cell, half prismatic. There's a rigid frame around the edges, but the face of the cell is flexible. When the battery is empty, the face is recessed, like a button pressed in. When you charge it, the face pushes out until it's flush with the frame. It's like a piston. The cell breathes in and out without pushing against its neighbors. Obviously, if you're thinking batteries, how you're gonna do it, leave space, like it's not like crazy, but the actual engineering of making this particular pouch work is actually pretty impressive. Now, let's talk about what this isn't, because let's be honest, there's a little bit more to this story. QuantumScape calls this a solid-state battery, and technically, half of it is. Is the QuantumScape battery, is it truly like liquid-free? Is there any electrolyte or equivalent in the battery?
So we have no electrolyte on the anode side, just lithium. We have a solid-state electrolyte that's our separator. On the cathode side, there's a material that we call a catholyte. That's the electrolyte inside the cathode.
So this really is a half solid state battery. The anode is revolutionary and the cathode is, well, it's pretty conventional.
Cathode materials don't conduct lithium well enough that they don't need an additional electrolyte. That additional electrolyte could be a solid, it could be a liquid, it could be a polymer, and there are different classes, even within solid, different classes. So some people are starting to say things like semi-solid state, hybrid solid state, all solid state, condensed state. None of these terms have a rigorous definition.
Sure.
But I think the most succinct answer to your question is there are architectures that are all solid. The electrolytes and active materials would all be solid. This would be an all solid state battery. That is very feasible. At the same time, I don't think people are going to buy a car because it has an all solid state battery in it, or a solid state battery, or a lithium ion battery. They're going to buy a car because it offers compelling performance. You know, what's its range? What's its charge time? What's its cost?
Does that matter? Well, for energy density and charging speed, no. Those benefits come from the anode side, and they're real. For safety, it's a little more nuanced. The ceramic separator is non-flammable. That's good. But there's still organic liquid in there that can burn. And metallic lithium is one of the most reactive metals on Earth. So if the cell gets punctured or hits water, you're generating hydrogen gas. But is it safer than a standard lithium-ion battery that we have today? Probably, yeah. Is it the perfectly safe solid-state dream? Probably not. But here's the thing. They never claimed it was. What they claimed was double the energy density, 15 minutes charging, and a real production line. And on those claims, they delivered. So color me impressed. I mean, QuantumScape has done it. They built a manufacturing process that nobody else has. They solved the death spiral, and they're shipping cells. Is it perfect? No, I think there's probably room for further iteration and improvement over time, but this is a massive step in the right direction. A lithium metal anode was something that we've talked about for a long time as a way to really increase energy density. It just was never really done before.
The two major classes of challenge are first the materials, and then second, a process to make the materials in the right qualities and quantities at cost. So from the materials point of view, there's been a lot of innovation for solid state materials that can conduct lithium. So that's pretty remarkable, and that's one class of challenge, is to invent the right material. But I think the even larger class of challenge is how do you process the materials that make a battery with those materials at the ultra low cost that's required for lithium ion batteries and not ultra high quality that's required to have, low failure rates and high cycle life.
Can QuantumScape automate the entire cell and pouch manufacturing like today's batteries? So this question is important because if they can't, and it's bespoke and requires human intervention, prices will never come down. So this is actually the breakthrough that we came out to see today. Their Eagle production line features custom-built tooling to automate the entire process from current collectors and separators, cathode, to the entire pouch. Here's the entire process. Their patented solid-state separator is adhered to a copper current collector we'll call side A. Then comes a double-sided cathode. Then comes side B, which is the same as side A except that the tab is reversed, so when they flip it over, the tabs align. Then comes another side A, current collector plus separator, and the whole process, the sandwich, repeats over and over until you have 11 unit cells in a fixed flex frame complete pouch. And let's remember that they have production lines and they're well on their way, but there's still a long way to go from where they are now to being able to supply these to millions of EVs every year. But there is some precedent. Last year at IAA Mobility, they showed a Ducati motorcycle fitted with nearly 1,000 of these cells. 21 kilowatt hours.
So one of the things that's very hard about battery development is you're playing with atoms. If you have computer software that you're debugging, you can step through line by line in a debugger and figure out where things went wrong. In the world of atoms, there's nothing like that exists. You can't watch where the atoms are arranging themselves and then go back and say, well, what if it went there instead? So it's a much more deliberate process of experimentation and observation that has to be done. That's fundamentally why it's slow. One opportunity is to bring more data to bear in this development process. So we do a lot of statistics, we collect a lot of data, we have machine learning models that run in our production line to try and extract all the data we can out of the experiments and tell us what we should be doing the next time to make it better. So I think that's a pretty powerful accelerant.
So does their business model work? This one's interesting because unlike Donut Lab, who wants to build the batteries themselves, a massive undertaking. That room we were in, that's a clean room. It's dehumidified and clean and free of dust particles because any little bit of particle will ruin the ultimate performance of that battery. That's not what QuantumScape is doing. QuantumScape is an R&D company. They want to build the technology, show how it can be scaled up, automated just like any other battery, and then license it to the big boys, the people who make batteries by the gigawatt hours already. That's a small distinction, but it's critical. That's what makes QuantumScape, to me, a really viable contender and a path forward because they understand it is one thing to build this and to be able to show that it works, and then to be able to build it for millions of customers around the world on a continuous cycle. That is another skill set that not every company has.
Is there room for even greater gravimetric? Is this like the first generation and like all things we would optimize and be able to get that up?
Yeah, good point. When lithium ion was introduced, it was less than half of what it is today, maybe a third. And it has increased on basically an S-curve that's starting to saturate as most of the materials innovations are reaching a natural limit. And so what we want to do is start our S-curve with the bottom of our S-curve being at parity or better than lithium ion and improve from there. And there are a lot of obvious ways we can improve. We've built out a technical roadmap that has improvements in many different technology areas that will improve our energy density, fast charge time, go to larger form factors as well, which is important for automotive.
2026 is turning out to be quite an amazing year for batteries. For QuantumScape then, I think they've approached this the right way. 15 years they've been at this. They started by finding that separator, that solid state separator. Then they realized it doesn't matter if we can't scale it at the rate of everything else, otherwise it'll be the limiting factor. And they've kind of solved that. They have the Cobra process to be able to manufacture this at scale. Then they showed that even though this is a little bit of a different makeup, anode-free, it's a different type of battery, that they can still produce it on a line from like individual collectors all the way to pouches. The next step. Now I think what is left is to identify their scrap rate. Now, this might surprise you, but every battery has a scrap rate. Even the big boys, the guys that make the batteries you've heard of, sometimes up to 25% of their final products get scrapped, meaning 1 out of 4 batteries that come off a line get tested and the internal resistance or storage or other characteristics aren't in line with what they need, and it gets scrapped, ideally recycled. What is that number for QuantumScape? We don't know. But I think with a novel technology like this, there's so much, right? That solid interface, that's a tough thing. And this entire process, I think that is the number that they're working on. So then if they can get the scrap rate down to the same level as traditional battery manufacturing, every company on Earth would switch over to use this. And we would see solid state, partial solid state batteries, anode-free, lithium metal batteries everywhere. But if the scrap rate is too high, you can imagine what it does to the price. And so if you're turning around testing cells and they're not quite there, that I think is what is left for them to sort out. Again, that's kind of my speculation here. We'll make more content as we learn more, but this is a pretty big deal for the battery world. But what do you think? Do you have any questions, by the way? I can try to reach out to any contacts we have to get them answered in the comment section. Let's keep this going. Sound off in the comments below. I'm Ricky Da Vinci. Thank you so much for watching.